Hello everyone, this is EMET. My group and I, which include Marvin and Adrian, did a research project on solar chimneys, which also are known as solar updraft towers, with more of an emphasis on the turbine power and efficiency, with our advisor for this project being Dr. Bart. A couple justifications for solar chimneys is that it provides energy which happens to be renewable. It is non-polluting, which means it is free of carbon emissions because it takes advantage of solar radiation and uses it as fuel. It functions day and night. At night, it takes advantage of water tubes that would be present. At night, the heat that was captured during the day, and at night, is released. These solar chimneys are a reliable source because there are few moving parts. The only moving part in a solar chimney is the turbine, transmission, and the generator. Another benefit of a solar chimney is to provide power to less industrialized countries. These chimneys are not high-tech. The chimneys do not need cool waters, and areas that are too hot do not need to have worry about water waste. With this slide, the figure on the bottom left shows measured power that is produced along the time of day. The figure on the right measures multiple solar photovoltaic variation. What photovoltaic is, PV, is how solar ray energy works. The Manzanares prototype, which was built in Spain, was used to measure the power output. For a dual-axis panel, the average energy production is 650 watts. A drawback to a solar chimney is the height, which determines the conservation efficiency as well as increase the initial cost of construction as well as maintenance. As mentioned before, there are three essential elements, which are the solar collector, tower, and wind turbines. The collector takes advantage of solar radiation by heating up the air, which then travels through the tower. As air passes toward the tower, it powers the wind turbine at the center. The material used for construction is very minimal for developing countries, which makes a solar chimney a good choice for an alternative power source. Only a few types of chimneys were tested, including one prototype built in Spain which lasted for about a decade. Solar chimneys will have a constant supply of air since the collector is open at the base. As stated previously, hot air passes through to power a turbine and to obtain energy. Solar chimneys are not only renewable because of air flowing into it, but also because air is an infinite supply that is also released from the top of the chimney. The power that the turbine is obtaining is also dependent on the orientation and position the turbine is located in the chimney. Our goal for this project is to design and test our solar chimney. The test would include the mass flow rate of air and the power that the turbine can supply. A couple challenges that we faced for our solar chimney were changing over the course of working on this project. The dimensions cannot be too big, even when using answers, which will be explained about later. The mass flow rate was going to be difficult to obtain as well. For our prototype, there is the use of research papers and computer programs. The main programs that we used were SolidWorks and the student version of ANSYS. These are some design restrictions based on industry. The Manzanares prototype gave an overall output of 44 megawatts in a year. Sadly, companies view this as too little power output to warrant this as a dependable energy source. The resources cost too much, and land may be more important for other uses, such as housing or for companies. The lifespan of solar chimneys is difficult to pinpoint. There is always the initial cost of building a solar tower. Then there is also the pricing maintaining said tower. Though gravity can cause the tower to break if ultimate compressive yielding is met. The land, however, can also double to grow plants, which allows for another very good resource, being food. With the use of ANSYS, we wanted to increase our model to be able to go full scale, which we would then increase the tower height to be around 1,000 meters, and the diameter would be equal to, if not greater than, 1,000 meters. Using the student version of ANSYS, however, we had to decrease the dimensions to be similar to that of the prototype that was built in Spain, and that still came with its own difficulties. These difficulties were the meshing of the model and the limit that the student version of ANSYS had for the nodes and elements. The images on this slide have our final dimensions for our prototype. The left one is the final dimensions for our turbine, and the image on the right is the final dimensions for our chimney. On this slide, we have our initial design for our prototype. Our turbine, which is on the left, would have been a computer fan. Our tower, which is on the right, would be made of a PVC pipe. Our collector would have been made of clear plastic. In order to successfully attain finite element analysis, meshing is a very important step that must be taken to ensure proper results are being obtained from finite element results. For the solar chimney's natural convection and radiation parameter, a high-quality mesh is required to perform our analysis. However, after testing several meshes, the size of elements and nodes had to be reduced due to the use of student version ANSYS limits by enlarging the size per element on a mesh. However, this reduction brought down the overall quality, which gives us a poor volume ratio between the nozzle and solar collector. The nozzle specifically suffered from obtaining a mesh of quality and fails to generate any further thermal analysis through ANSYS Fluent. As we continued to investigate and research, we found that a hexahedral mesh was the best way to perform ANSYS with our model. Unfortunately, this mesh is unavailable through ICEM CFD commercial license software, in which our student version did not give us the ability to use. We tried to build a similar mesh with hope Fluent Analysis will accept it and let us run analysis in our model. However, we kept running into issues with the student license we had. To ensure proper hexahedral mesh, the geometry was built only with 3 parts and defined as 3 body parts for meshing. The 3 body parts consisted of the solar collector, the tower, and nozzle. The parts were constructed as a 3D sketching using ANSYS Fluent software and revolve around the y-axis. When you look at the top left table, it showed our dimensions that we used for ANSYS, which is quite large for the student version when you are trying to input the meshing, because there would be so many elements and nodes that ANSYS will create. There will be different material used for the collector, the tower, and the nozzle. The table on the bottom right shows each of the properties of the materials that would be used in our tower. So the air is the air that is flowing through the material. The concrete is what the tower and nozzle is made by, and the collector is made of glass. In order to investigate the mass flow of air, temperature, and density across various locations of the tower, the first assumption will be that air is treated as an ideal gas. That is because the solar updraft tower energy begins with natural convection and then changes between hot air and cold air density, so the mass flow of air depends on the changes in density between cold and hot air. The negative gravity of 9.81 meters per second squared on the y-axis is placed. The radiation model was also configured to a surface-to-surface analysis due to the enclosure of the geometry in order to study the orientation and energy transfer throughout the three body parts. In order to limit the computational analysis as much as possible due to the student version, we increased the clustering model to 4 faces per surface in order to reduce the amount of faces being simulated for energy data. As shown in this slide, we placed a thermal boundary on the solar collector with natural convection and radiation, and only temperature boundary for the rest of the other walls. As shown on the slide, we placed a thermal boundary on the solar collector wall with natural convection and radiation, which is the first table. So you can see we put the heat transfer coefficient, the free stream temperature, the external emissivity, external radiation temperature, internal emissivity, and wall thickness. There's only temperature boundaries for the nozzle wall and the tower wall, which shows the temperature, the internal emissivity, the heat generation, and the wall thickness. The objective of the design was to build a prototype with a smaller scale version of the dimensions used from the Spain prototype solar chimney tower, in order to test for its turbine efficiency at different locations of the tower. A turbine was to be placed in different locations of the solar tower to study and experiment the turbine's potential power generation and efficiency. The efficiency was assumed from theoretical models used by various researchers, since no running prototypes were available to gather data. ANSYS would also be used to go through computational fluid dynamics to determine the mass flow rate. Again, there were limitations due to the use of the student version of ANSYS. The two equations shown on this slide were for our analytical values. Experimentally finding the mass flow, temperature, and density of air throughout the tower would have been very useful, because this would then allow us to have been able to calculate the turbine efficiency and power. Our tower research provided many equations. These three equations on the right explain how power is provided. The collector provides a mass flow rate. Q double prime is the heat flux. A is the cross-sectional area of the collector. Mass flow rate will increase with the increased diameter of a collector. H is the enthalpy of air flowing under the collector. H1 is the air that is entering the collector, and H2 is the enthalpy at the center of the collector. Once the mass flow rate is solved for, we assume the mass flow rate is the same that is going into our turbine. Pn is the air pressure that is about to enter the turbine. H is the head loss that is due to the turbine. Pout is the air pressure that exits the turbine. It also happens to be the pressure that enters chimney. For the chimney, we found a modified Bernoulli equation. With these three equations, and there are more equations, about 14 in the previous slide that had one of the reports we used. Once the unknowns were solved through ANSYS and an engineering equation solver, the unknown values will then be compared with published data. Determining the price on this prototype was very difficult, since This prototype would be in Spain. The land would cost about $372,000. The turbine, solar chimney, and transporting these materials would cost over $600 million. This initial pricing is what most people look at when determining if a solar chimney is worth building.